We just saw what happens when you apply an AC voltage to a resistive circuit. Now let's see what happens when you apply an AC waveform to an inductive circuit. So here we have an AC source and this source is driving an inductor. Let's say that the instantaneous voltage of this source V is given as Vm sine omega t. If you were to apply Kirchhoff's law to this particular circuit, you would notice that unlike the DC case where voltage and current remain constant, in the AC case the voltage and current are changing continuously. Now when you apply a time varying voltage to an inductor, the current across it is changing, and because the current across it is changing, it will develop something called a back EMF due to its inductance. The back EMF, as the name suggests, always opposes the change that is causing it, so it will have a negative sign. With this information, we can come up with the voltage relationship inside this particular circuit as something like this. We can write that V minus L di by dt is equal to 0. Here L is the self-inductance of the inductor, which is normally shaped in the form of a coil. V is the source voltage and di by dt is the variation of the current with respect to time. So here we have di by dt is equal to V upon L. Now V can be written in terms of the peak voltage, so we can also write this as Vm sine omega t divided by L. Here we have a time changing relationship for current. If I want to find out what the current is, I will have to integrate this relationship with respect to time. So here we apply integration. So di by dt integral is equal to Vm and L are both constant, so we can take them out. So this becomes Vm divided by L sine omega t dt. So here we have I, this is equal to Vm divided by omega L cos omega t, here's a negative sign, plus C. Now C is the constant of integration. Since we are dealing with a current equation, C also has to be a current. In this particular case, we are assuming that at t equal to 0, when we started this experiment, there was no current flowing in the conductor, which means that this term becomes equal to 0. So we can disregard it. So we remove it here. And that leaves us with the rest of this equation. I is equal to negative Vm upon omega L cos omega t. We can rewrite this equation by converting the cosine equation into a sine equation. So this becomes, using the relationship, negative cos omega t is equal to sine of omega t minus pi by 2. We get to write this equation as I is equal to Vm by omega L sine omega t minus pi by 2. Now let's try to understand what this current equation is telling us. Here you can see that we have the quantity Vm, that is the peak voltage provided by the voltage source, divided by omega L, and then we multiply it with sine omega t minus pi by 2. If you compare this equation with the equation for current in a resistive circuit, you will notice that Vm upon omega L looks very similar to Vm divided by R. In other words, this term omega L is performing the same function in an inductive circuit that R is performing in a resistive circuit. They have similar roles, but they are not the same. In both cases, these quantities are controlling or regulating the amount of current in the circuit. But there is an important difference between them that we will understand shortly. So this quantity here, omega L, can be written as X subscript L, and this is known as the inductive reactance of this circuit. We will not call it a resistance because it is not behaving like a resistance with respect to the power dissipated in the circuit, which we will see shortly. So XL is performing the same role in an inductive circuit as R performs in a resistive circuit. Another thing that we understand here is that if we were to increase the value of omega, if we increase the frequency of the voltage of the AC waveform, this entire term omega L will increase. So inductive reactance will increase with respect to the frequency of the AC waveform. If the AC waveform has a very high frequency, an inductor can generate so much inductive reactance that it basically becomes an open circuit. Now, we have found the current relationship for an inductive circuit, but what about power? How much power does this circuit absorb from the source over any given cycle? Let's see. For any closed cycle, we know that power is equal to V multiplied by I. If we adapt this basic equation to this particular case, the power dissipated instantaneously across the inductor can be written as Im sine omega t minus pi by 2 multiplied by Vm sine omega t. So here we have the instantaneous value of current, that is Im sine omega t minus pi by 2 multiplied by the instantaneous value of voltage, that is Vm times sine omega t. We can rewrite this equation. Since we know that sine omega t minus pi by 2 is equal to negative cos omega t, I can write PL as negative Vm sine omega t. So this comes to negative Vm Im sine omega t cos omega t. We can try a little trigonometric manipulation here. Let's multiply this equation and divide this equation by 2 on this side. So we have negative 2 Vm Im sine omega t times cosine omega t divided by 2. We can take out the constant terms, so this becomes negative Vm Im, and you may know that 2 sine omega t cosine omega t can be written as sine 2 omega t. So this becomes sine 2 omega t divided by 2. This gives us the instantaneous power across the inductor at any given time in this circuit. If I wanted to find out what is the average power, then I could take the average of this particular signal over a time period t, as we had discussed earlier with the resistor example. For a sinusoidal function like this, for any closed interval of time 0 to t, for any closed cycle, the average is equal to 0. So we get that the average power of an inductor is equal to 0. There is no power dissipation in an ideal inductive circuit. The reason for this is whatever power is absorbed by the inductor during one half cycle is returned to the source by the inductor during the next half cycle. No real world inductor can work like this because all real world inductors have resistance. So the dissipation happening in those inductive circuits will only be because of the resistance in them. The inductor itself will not absorb any power over any closed cycle. And this is the major difference between inductive reactance and resistance. Reactances do not absorb power for any closed cycle, but resistances do.
Manorama Horizon. Learning made simple.